Yes.
Great.
All right.
It's really nice to have Mark Brodsky. He's going to tell us about the power of trees.
All right. It's been a while since it's been quite a while since I've been here even for a visit, but I appreciate the welcome and invitation. It's nice to see some of you again and to meet some new people possibly. Thanks. Last time I was here, oh, well, definitely before COVID, and I think is that how we define New World things in the world? But I think even long before that, I tried to get the last give a seminar talk in 2018 or 17 here. Yeah, something like that. Yeah, that what it is. Yeah. Thank you. Thanks also. Thanks for the invitation to come back here again, and glad to be here. All right, so we're going to talk about the power of trees, and trying to remember how this how to start. We're going to start with the blackboards and moving up and down and everything. All right, we'll start. It's a matter if I start in the middle. Is there a intended sequence? I can't remember how it works. No matter where I start. Start in the middle. Doesn't matter. It's okay. All right. The power of trees, and this is joint work with Asaf Rinot, whom many of you know very well because he used to be here and is certainly known around the world, and Shira Yadai, who is a student of Asaf, who is showing quite a bit of promise in terms of set theoretic development. All right, so we're going to talk about features of structures that are not maintained, not preserved by products. Okay, focus on features of structures not preserved by taking products. Okay, we talk about topological features. The simple example, just to review sort of some basics, we've got the Sorgenfrey line. What is the Sorgenfrey line? So it's a normal topological space whose square is not normal. So we can just put that here. Normal space, should I say topological space, whose square is not normal. And that is provably exists, can be shown to exist without any extra axioms. If you add some extra axioms, you can talk about the Dowker space, or a Dowker space, not the Dowker space, a Dowker space, meaning to say, which is a space that is normal, but, or I should say,
Dowker and Dowder are the same person.
Sorry, that was a typo, misprint. Dowker. Normal, we can call it X is normal, but X cross the interval, unit interval, is not normal. Okay, and the thing with the Dowker space, what Dowker specifically showed is that X is Dowker if and only if X is normal, but not countably metacompact, countably metacompact. We have the problem with running out of space on the blackboard. I hope that's legible. Not metacompact, where and then the whole history of Dowker spaces is involved, which I'm sure, well, some people here can tell it better than I can, but basically Mary Ellen Rudin derived the Dowker space from a Suslin tree even before Suslin trees were known to exist. That turned out to be profitable because, of course, now we know Suslin trees consistently exist, and so Dowker spaces consistently exist. Later on, there are Dowker spaces shown to exist without any extra axioms or assumptions, and there's lots of research into Dowker spaces with particular cardinalities, particular properties, and so that's a bit of the history on one foot of that. Or significance there, but on its in the simple sense, a Dowker is a space that is normal, whose product with a particular normal space is not normal. Okay, so one of the things we're going to ask is, oh, well, let's just talk about a few more properties here. So, oh yeah, CM, right. So let's just clarify because it will be interesting to talk about. Sorry. What is this the one that's going to go up after? Yeah, okay. We wrote here countably meta-compact. So let's talk about that. And countably meta-compact space is countably, since we mentioned it, and we're going to talk about it some more. Meta-compact means, okay, if every countable open cover admits a point finite refinement, open cover admits point finite refinement. And there are other equivalences you can also talk about, even when Dowker showed his original equivalence proof that if it's not, it can be normal but not countably meta-compact is also the same as normal but not countably paracompact, I think, or the few other, what? Yeah, countably paracompact. So there are a few other equivalences there. But every countable open cover makes a point finite refinement. So we've got all these sorts of weakenings of compactness that are useful for precise characterizations in various ways. But one of the reasons this is going to be interesting for us is we can talk about a strengthening of it stronger than CMC, which is countably meta-compact, is perfect. Should underline some definitions here. Countably meta-compact, perfect, which is that it's all closed subsets are G delta. Are there any longer pieces of chalk, or is this how they always are?
Yeah.
Oh, that's what it is. Okay, I was using the remnants here, and I was trying to figure out what's going on here. Oh, I see. Oh, good, great, thanks. That's helpful. Okay. All closed subsets are G delta, and even stronger is perfectly normal is perfectly normal, which is just perfect and normal, I think, right? There we go. Okay, so the main questions that we're going to deal with, the main question that we're going to deal with is, can we get the various of these various such properties that we've mentioned to hold for trees with the interval topology. So we'll talk about that. Special interest. Squeeze it down here. Go onto another board. Here we go. Of special interest. Okay, is whether the various properties above properties mentioned, so it's not literally above but to the left, various properties mentioned can occur or can be maintained in trees with the interval topology. And I'll define that shortly. There are various ways to define a topology on trees. One of the most natural ways is the interval topology. I'll define it in a few moments. But the most possibly a striking result here, although we mentioned here somewhere Dowker space. Why did I not underline it? But that was a definition. We mentioned here Dowker space. Although Dowker spaces, as we said, can be shown to exist in many different ways and with many different properties, but a tree with the interval topology is never Dowker. So we'll mention that down, and we'll mention that down. Write that down here. It's a fact. Okay, a tree T with the interval topology cannot be Dowker. That's due to Nyikos, it seems. Should put that in here. Fact, Nyikos. So we're not going to construct any Dowker trees, but we are going to talk about is what of these, we're going to talk about the question of trees being countably metacompact. And we're also going to focus here on how we can control the square of a tree, the properties of a tree and its square differently. Okay.
When you say tree, do you have any restrictions on how tall, how wide, what?
We're going to focus on trees of height omega 1, on omega 1 trees in particular. But I think the claim of Nyikos is pretty general. But our focus on constructing trees is going to be on omega 1 trees in this case. Okay, so what kinds of trees? So let's talk. So we can nix from the outset, trying to get a tree that's a Dowker space. That won't work. So we can talk about. Let's talk about metacompact. And what we know is, so let's talk about some aspects of trees. Okay, some aspects of topological aspects of trees. An anti-chain of a tree is closed discrete. Okay, and so it follows that if T is a special tree, we'll talk about special omega 1 tree is a special omega 1 tree, or really of height, any tree of height omega 1, then the tree with a tree topology, then it will be perfect. I should have said with the interval topology. Maybe I should here let's define the interval topology before we go further so we don't get mixed up here, so we know what we're talking about. Oh, I messed up the nicely clean board here. Okay, so let's just put it down so we don't get mixed up. First of all, to answer your question, let's formally describe what trees we're talking about. In our context, the trees. Okay, what is going to be a tree? We know there are abstract definitions of trees, but we're going to focus on trees. Since we're going to construct trees, we're going to want them to be of a particular form. We're going to essentially be constructing trees that are what you might call sequential trees, or we might call streamlined trees. Let's just say a tree is a set or a subset T of sequences from countable ordinals to omega that is downward closed. Okay, the subset T, I could say, doesn't matter. Okay, that is downward closed. Okay, meaning, hopefully people can, that for every T in the set T and every, let's say, beta less than the domain of T, meaning the length of the sequence, T restricted to beta is also in the tree. All right, so we've got our downward closed trees. And so when we talk about the height of an element in the tree, for us, it's the domain of the sequence. All right, and height of the tree has the obvious meaning. The T alpha, the alpha level of the tree, you can think of as the T intersection functions from omega into, sorry, from alpha into omega. Okay. So yeah, the interval topology. What is the interval topology on trees? What is an interval on a tree? Okay, for any two nodes or any two sequences, you can call them X and Y, where X is strictly included in Y as a sequence, both in the tree T. Okay, we get the interval. The interval, and you got to write it like X, Y, it's sort of a half open, half closed thing. That's what we're going to call open. The interval is what we call open, is what we declare open, is what we declare to be a basis element, a basis set, basis element, I guess. And you also need something including the root. Also. Okay, so we've got our basic open sets for the tree topology. So that's what we call the interval topology. This defines, this generates. The interval topology on T, and we will call it xt. When we want to emphasize that we're talking about the tree with its with the topological space, the interval topology, we'll call it xt. So that's our basic setup here. All right.
So this is all of the nodes that are between X and Y, right? Y is longer, and it's all of the restrictions of Y.
Right. You're right. Yes,
So
correct.
it's not like another thing that you could do, maybe, I guess you could take some kind of lexicographic interval where you could look at the least difference and look at things between them.
Yeah, there are a lot of different ways you can generate topologies on a tree. As somebody mentioned a few minutes
But
before.
if this is the definition of tree, I guess I'm wondering why our trees are well founded. It seems like this notion of interval in a tree. I mean, of course, we love well-founded trees.
Yeah. No, the
That's
tree,
an omega
the tree
one.
itself is well. Hang on. The tree, as a set theoretic object, the tree is a collection of sequences.
Yeah.
With
Yeah,
the
yeah.
with the ordering, with the natural ordering on the sequences inclusion, which
Yeah.
makes it a well-founded
Which
set
makes it a
theoretic
well-founded
object.
tree. Yeah, sure.
Now, as a topology, we want to define the topology based on these things being the open sets, so that the point is you want nodes at successor ordinals or non-limit ordinals. Every individual node is open, and for the ordinals at limit levels, you need to have something below it in order to get an open set. So something of this form, including some y, for example, at a limit ordinal, you got to get some thing below, well, the x below it to say everything above there is part of the open. I'm not sure I got your question really,
So
though.
I guess it seems like this notion of interval topology makes perfect sense on any like ordering that I would think of as a tree. Like where it's a partial order where the predecessors of any point are linearly ordered.
Exactly, yes, you need it. Yes.
Okay, I haven't thought about it too far. Maybe, I mean, he's saying you're right.
Ordering on your trees yet.
Okay. Then I should have said. Okay, so I missed that. Let's say. Oh, was that the problem?
That's not the confusion.
That's not your question. That's okay. Well, let's just say it here. Okay. Sorry. So let's clear up the simple part first. Let's say it explicitly. Right. The tree, the ordering.
Just pointing out the first step.
Yeah, I think
The ordering is.
Of course, we all love a good omega one tree.
Yeah, but you're saying that interval topology is well defined, not only on trees.
Like, no, I mean on trees that happen to be not well founded.
Okay, haven't
Like
thought.
a real line.
For example.
Okay.
Yeah. Right.
Well, I think okay. Well, I mean, the question. Well, okay. The question then becomes: so what? So on a linear order, that's true too. Question then is that the half? What's it called? What? But then the question: if you do it on the real line, then what does that give you? Is that the Sorgenfrey? What does that give you? The Sorgenfrey? But
the point about this closed thing at the end, if you take the successor of y, it's still an open interval. So this is the same as just the usual linear order topology. Because
No, there are no successors.
yeah, but not on the real line. But not on the real line.
Yeah, so I know, but here it does. So this half closed, half open interval is really just an open interval.
Yeah. Well, we're declaring it to be open.
No.
But it's
Oh.
an interval with a different
Immediate
y.
successor of y.
Yeah. If they're assuming there is one.
It's not maximal. Yeah,
It's assuming we don't have leaves. Yeah. Okay.
Why is maximal? This is what you would do in the linear order
Right,
case
exactly.
anyways.
Okay. I think part of the problem I had once, and I mentioned way back in my PhD thesis, I put a footnote there saying it doesn't generalize well to arbitrary partial orders. But clearly there are some things that are not trees for which it can still be useful or meaningful.
Like, yeah, so like you can take the real line, and it's a perfectly good construction of topology on the real line.
It was mentioned already.
And it's on the board. So this is, yeah, okay, good. So that answers my question about well-foundedness, I think.
Okay.
that it is meaningful to think about non-well-founded trees, like linear orders, like the real line. Great.
Yeah, okay, fine. Yeah, okay, good. I'm not sure how well I answered or how well we somehow jointly figured it out, but I'm glad that works. Okay.
My silly point is it's also the same as, if you define it different, it's the same as the usual topology.
Okay, so yeah, you could make a choice between, okay, how the generalizations work exactly. Okay, all right, let's get to some oh yeah, points. So now we understand what the interval topology on a tree is, so we can go back and restate what did we just say here? Right, a tree with the interval topology. Okay, so all right, a tree with the interval topology cannot be Zauker. So the question is, what can we get trees to be? Let me go back to where I was here. And so I started to write, and then I replaced. Let's move over here. Right, any anti-chain. An anti-chain of a tree is closed discrete. That's not hard to prove. Closed discrete in the interval topology. So if T is special, then or I should say a special Aleph 1 tree. Yeah, special. Then xt, the interval topology, is perfect. Okay. And we're going to try to look, we want to look for spaces that are not CMC. So this is going to rule some out. Okay. And almost Suslin trees, or Aleph 1 trees, are countably meta-compact. That's another result from Miaikos. And another thing here is that if you have an R embeddable almost Suslin. Why are we talking about almost Suslin? Well, I can't talk about Suslin if I want it to be R embeddable. So it's almost Suslin here. R embeddable almost Suslin Aleph 1 trees are perfect. So, pardon?
Thank you.
Okay, I should give a definition. Yeah. Almost Suslin is that I guess I should write it down. So we know Suslin is, of course, that an anti-chain has only countably many, every anti-chain is countable. So here, almost Suslin is that the levels of the nodes in an anti-chain form a non-stationary set. So it's a weakening of almost Suslin. I guess I can. I can write it down now. I was going to write it down later. Make sure we got it right. Okay, let's put it, say, definition here. An Aleph 1 tree is almost Suslin if for every anti-chain A in T, the set of the height, what we call domain of the nodes, domain of X, again, domain of a node is its height, because we're thinking of the nodes as sequences, for the X in A is non-stationary.
So if you have a Suslin tree and then force with it, then what you get is that almost Suslin?
No, you have a branch.
1 second.
No, but anti-chain, it's just about anti-chains. And the only anti-chain I can see is the non-stationary.
No, you go
Say
off to
again?
the side, but then you keep the node on the, you also keep.
Yeah, of course, yeah, sure. You're right.
Yeah.
No, but you're right.
Yeah, that's true. I'm not quite.
But you can take something off.
Yeah, just go to next.
All right. So we've got a weakening of Suslin that turns out to be possibly.
Almost. It's an Ehrenstein tree.
Well, no, it once said no, not by definition, because there are some constructions of almost Suslin trees that are Kurepa. You can have an almost Suslin Kurepa tree. So you can have lots of branches if you so want. It could be that the usual case is more to specify that you want a branchless, an Ehrenstein almost Suslin tree, but one should specify. It could be the various definitions. I mean, I think we'll keep it at this. But it's true. Many applications, what you want to construct is an Ehrenstein tree that's also almost Suslin.
Yeah.
Well, okay. It's okay, fine. But again, what? You mean the chain itself? Yeah, okay, like anything. The trees are generalizations of, okay. Choose your preferred definition if you want to exclude the trivial cases or whatever. What? You think, yeah, that's the first thing of it. What? Yeah. Yeah. Okay. So R embeddable trees are, what did I just say? Sorry, if a tree is almost Suslin and R embeddable, an Aleph 1 tree, then it's perfect. In most cases, we always have some way to exclude the single branch, right? So in this case, R embeddable. But anyway, so we've got all kinds of trees of various kinds. So in particular, a special Aleph 1 tree is perfect. And the almost Suslin R embeddable tree is perfect. If we want something that's, and perfect is stronger than CMC. If we want something that's not CMC, so we're saying it can't be special, and it can't be, and it can't be almost Suslin, essentially. So well, that's part of what we're talking about. That's part of what we're going to try to construct. I mean, the goal is to get something that's not CMC. So, no, I think it is. I have to remember what there are. Maybe I've got references to who's done it, but we'll see if we can talk about that. Yeah. Lost my place again. What was I saying? Did we say what's this? Yeah, sorry. Okay, I do have it here. Fleissner gave some a non-CMC Aleph 1 tree. Okay, so the point is the result here, or sort of conclusion of this sort of discussion, is that we can a non-CMC Aleph 1 tree is quite unusual, as it can be neither special nor Suslin. Neither special nor Suslin, right? Nor almost Suslin, even. And Fleissner constructed one. Okay. And also I'll write this name, and then maybe Frank can give me an approximation of how to pronounce it closely correct. Is it Hanazawa? Okay. All right. Also, Hanazawa constructed a non-CMC tree. Sorry, a non-CMC Aleph 1 tree. This one was from Diamond Plus on Omega 1, and this one was from Diamond on Omega 1. Okay. What we want to talk about here is okay, extending these results to control not only the tree topology, or the interval topology on the tree that we're constructing, but also its square. Okay, and in an independent way. And so the idea is that hopefully we can develop some machinery to do tree constructions where we can obtain certain prescribed properties for the tree itself and different, apparently opposite or seemingly opposite prescribed properties for the square of the tree. Essentially trying to do one independently of the other. And there are many ways we could choose to do what to do for the tree and what to do for its square. So we'll try to state a theorem that is the one that we're going to, well, almost the one that we're going to focus on. I'll qualify that shortly, but let's state a theorem here. This one's better. Okay. So we've got a main theorem. Let's see what we can state here. Here we go. All right, theorem 1. Suppose that we've got diamond star on omega 1. Then there exists an R embeddable almost Suslin omega 1 tree such that we'll call it T, such that xt is perfectly normal, but xt squared is not CMC, countably metacompact.
So by diamond star is one where you trap on a club, but you don't trap the club that you're trapping on. So,
Right, as opposed to diamond plus, which will be even stronger. So it's an intermediate between diamond and diamond plus. But it allows us to control things on a club, not just on a stationary set.
Is xt squared normal?
So that was the that was a question to think about ahead of time. Xt squared cannot be normal. I think we'll see also if it's not CMC. We talked about the fact that Dowker space, a tree cannot be a Dowker space.
This tree product?
Well, okay, so we gotta say what exactly is the tree. It's not quite the tree product. It's the topological product, but it ends up being that a lot of these things are preserved by the subspaces. And so we'll have to check exactly, but it seems that this, so let's just put it here as an aside.
It's a subset of
No, pardon?
x sub t squared, the way you take the tree product.
Okay, is a subset, subspace. Yes, essentially. I'll define those precisely, but yes. Yeah, all right, I guess so. Okay, is not CMC, and so we'll say also not normal. Okay. Okay. Now this is the main result. I have to say so this is the main result. It's and we'll talk about the construction and how we get to it and everything. Just trying to think what other definitions we need, but I'm going to point out here also that there's a little bit of cheating that I'm going to do. Let me explain that here before I get to the proof. Maybe I should have kept it here, actually. Let's just say theorem 2 is like theorem 1, but without the claim that xt is perfectly normal or is normal. And the reason I'm saying that is because the proof that I'm actually going to show you is the proof of theorem 2. It's close to theorem 1. Gets us almost there. There were some significant hurdles in getting from theorem 1 to theorem 2, which required a whole bunch of overhaul. I guess, to be honest, dealing with Asaf and Shir, we were working on it. Asaf spent 2 weeks intensely getting the breakthrough to theorem 2 rather than just theorem 1. And we have written it up, but it's a bit.
I don't understand.
Sorry, getting to theorem 1. Sorry. Theorem 1. Theorem 1. Sorry. Asaf spent 2 weeks intensely getting to. We had theorem 2 first, and which is what I'm going to prove to you now. Asaf spent 2 weeks getting intensely focusing on and eventually getting the breakthrough to prove theorem 1. I guess I could have numbered them oppositely.
So the only thing that's dropped between theorem 2 and theorem 1 is normality.
It's the normality. Yeah, I should have said. All right.
That's okay, no, it's okay.
It's just
Without
without the.
it's just
Yeah. So let's
example,
just say without normal. Exactly. Okay.
One remark might be worth
Yeah.
doing. I didn't know until I read that paper of Nyko's.
Mm.
So with this interval topology, these omega-1 trees are rather nice topological spaces, namely locally compact first countable.
Okay. Well, okay. I mean, Hausdorff. Well, Hausdorff comes from the definition. As soon as we define a tree as sequences like these, then they're automatically Hausdorff, and those are the ones we're considering here. It's true, trees in general don't have to be Hausdorff, but these ones will be. And what were the other properties you said?
Locally compact is obvious. You just have ordinals, closed ordinals.
Yeah. Okay. And first count. Okay. All right. So all right, these stand because omega 1. All right. Yeah. Okay. Thanks. Yeah. It's good to know. So we're going to prove theorem 1. We're going to prove theorem 2. There were some. So we'll talk about the proof of theorem 2. As I said, theorem 1 is proven in the paper that we put together, but I'd rather just focus on the theorem 2 proof here. Okay, so let us see what are the preliminaries that we need here. We've defined things like tree and all the basics there. Everybody knows what an anti-chain is. Is there any point in talking about things like that? I think, okay, fine. And almost Suslin we've defined. R embeddable might not hurt to mention, but let me just see which set of how I'm going to do this here. Okay. Okay, so one property that's going to be useful here is what we're going to call finite to 1. Let me just see if I missed something here. Okay, so we'll define, in order to give the proof of theorem 2, we're going to define a couple of at least one extra concept here. We'll say here, okay, a tree T is finite to 1. Remember, we're thinking of our trees as sequences. Okay, so we'll say here, this means for all x in the tree, remember that x is a sequence, okay, and n less than omega, the x inverse of all the numbers up to n, okay, is finite. Okay, so the idea is here that pre-image of any it's effectively pre-image of any finite set of ordinals is only a finite set, and so it's a clear proposition. I don't even know if we proposition. This is going to be our way here of getting the tree to be R embeddable. We just say, okay, every finite to 1 tree T is R embeddable. I don't think that should be difficult. People need to sort of unravel the definition of R embeddable. It's reasonably straightforward. Okay, let's talk about what we mean by the square of the tree, just to clarify, because we're actually going to have two kinds of squares here, possibly. Let's just state it properly. Two types of square. So let T be a tree definition. Let's formalize this.
So why is it
If you take the pre-images, if you sorry, just take the cardinal. Okay, maybe it's not. Maybe it's okay. I can write it down. Maybe it's not entirely obvious. I should write down. You can get a map into a lexicographic into finite sequences of natural numbers. Get a map into finite sequences of natural numbers. Sort of like into a Cantor set. Should I write it down?
No, don't write it. I thought it was something. It made it sound like.
Sorry, I made it sound too simple. It's
That's
not.
the definition of art.
No, sorry. I made it sound too simple. It's not quite that simple, but it shouldn't be complicated. Okay. Let's just put a definition here of two types of square. Okay. Let T be a tree, or suppose T is a tree. I think I prefer suppose rather than let. The word let is often overused and has many different meanings. So let's say suppose T is a tree. Okay, so when we write xt squared, which we have written already once before, at least up there, okay, this is the topological product space. Okay. Topological product. Sorry, okay. Okay, you've got the tree topology times itself. But when we write T squared, okay, we're referring to what is essentially a subspace of the product, specifically, or this is really referring to a set, okay, stands for the set. So we want to talk about of pairs from the tree. And the point is, when we take a product of the tree with itself, we want the two nodes to be at the same level. Okay, so every pair comes from nodes at the same level. And so we can write that as domain of x0, meaning the length of the sequence, equals domain of x1. Okay. And given with the ordering with what should be the usual ordering on what should be the tree ordering on this collection of such pairs is the usual expected thing, and we'll call it okay, the order, the square of the sequence extension order. Where do I write it here? Okay, so x0, x1 is in relation with y0, y1, the expected thing, right? If x0 is extended by x1 and y0 is extended by y1. Okay, so that's our usual ordering. And the point is that this tree order, let's write it down here. I'll do this here. So this tree product, this square, this sort of square of the tree in the tree sense, is a tree in the abstract sense. Hang on, and it's a subspace of the what somebody said before. It's a subspace of this one here. We'll say more. It's a closed subspace. Hang on. Let's do this here. What was I going to say here? Okay, so we can call these remarks. What am I going to say? Okay, so T squared with that ordering is a tree in the abstract sense. I'm just saying abstract sense because we've defined trees here to be something in particular, which you might say this is not, but in the usual abstract definition of tree, this is. And anti-chain has all the usual meanings and everything like that, but a couple of standard facts. Okay, so this T squared is a closed subset or subspace of the square on the tree topology. So comparing the two things we sort of defined here. And what else can we say? Every anti-chain let's write it properly. Every anti-chain in T squared is a closed discrete subspace space of, well, I can say of T squared and therefore of, actually it's a bit better just to say of xt squared. Okay, this is a standard fact about trees. This is nothing specific really about the square. This is standard about trees, so that should be okay. Okay, so let's get down to the is anything sort of, this was sort of all really still preliminary stuff. I think we're ready to get down to some more actual machinery that we're going to use for the proof. Oh, I can still slide up here, right? Okay, so the question is, what are the tricks? How do we get this ability to build a tree, construct a tree, controlling the properties of the tree independently or separately from the properties of its square? Okay, so let's talk about some of the tools we're going to use here. We're going to talk about something we're going to call an elevator. Elevators here. Elevators. Which version am I doing here? Before we do that, we'll talk about a tree coarsening. Okay. Definition. All right. For a tree T, we say that a partial ordering, a new partial ordering with a new symbol on the square of the tree is a tree coarsening of the usual square on the ordering, the usual ordering on the square of the tree, if for all pairs x0, x1 and y0, y1 in the square of the tree, we have the following conditions. Okay, we want to say that if x0 and x1 are in this new relation with y0 and y1, then they have to be ordered in the usual relation as well. Okay, so that's the simplest meaning what we mean by coarsening. Just a couple of other technical things to add in to make sure we don't lose the usual things we want. You want some sort of symmetry. If x0, x1 is in this ordering with y0, y1, then the reverse should be true as well. You should be able to switch the order of the pair. x1, x0 should be in the ordering with y1, y0. And finally, if x0, x1 is in order with y0, y1, then for any beta that's between any ordinal between the heights of the two, the restrictions should also maintain the ordering. So then for any beta such that the height of x, so beta is between the height of x0 and the height of y0, we have x0, x1 should be in the ordering with the y0 restricted to beta, y1 restricted to beta, and that should also be in the ordering with y0, y1. So you kind of get this sort of anything intermediate should not mess up the ordering. Okay, I think I wrote that correctly. Yeah, right. If you've got two nodes, I mean that I just right and some pair here and some pair there, and then something in between. So if this is in order with that, you want to maintain it all the way. If this is in order with that, then so is this and so is that. Pairs. Does that seem reasonable? Okay, we're going to define, let's move over here. Okay, we're going to define a collection of open sets above any node in the tree. All right. Okay, based on to do with the finite to one property. So let's say here, okay, definition. Okay, for all, for any natural number and any element of the tree, or any, I mean, essentially we're going to do this for elements of the tree. We can state it generally for any a sequence from a countable ordinal into the natural numbers. Okay, it's because we're just defining the notation here. We're going to denote u of nx to be the sequences of the similar form, but that extend x. So y extend x. I think I'm going to put here the strictly extends x. That's not so crucial whether you include the x or not, although we want it to be an open set. So let's say it strictly extends x. And the y inverse of everything up to n is within domain of x. In other words, we want it to be that when we extend the sequence above, and we're starting with x, we extend the sequence above x. Anything that we add will not go into natural numbers below n. Okay, so in other words, we add no nothing in our, we constrain what we have below n. Everything that we add above x should go into numbers n or above n. Okay, and now we're going to talk about one of the most crucial things here is an elevator. Okay, this is the definition of elevator. So here we define this, what we're going to say here. Okay, what do we have here? For a natural number, a tree T, okay, a tree coarsening, of the usual order, as we've defined what a tree coarsening is, okay, and ordinals, let's say beta and alpha, both less than the height of the tree. Okay, we're going to talk about a function. We want to be able to talk about functions from one level of a tree to a higher level of the tree, and talk about desirable properties that some functions will have. Okay, and so that as we build our tree, we want to make sure that there's a sufficient supply of functions like these to be able to get us to maintain the properties that we want and continue the construction. All right, so a function E, we're going to call it, from, I could say from T beta, or in some sense we want it to be more general, from a subset of T beta into T alpha, is called, or is said to be, is called an N elevator. An N elevator, and there's an implicit with respect to the ordering as well. We won't always say that, but it's implied. Okay, if what? If it satisfies these properties, two properties here. For every x in the domain of the function that we're talking about, okay, E of x should be an element of that open set that we've just defined above. So we want to be sure that what we add above the height of x, when we're going from beta to alpha, doesn't go into any natural numbers below n. Okay, and for every x0, x1, for every pair in the square of the domain, we want to ensure that x0, x1 is in the ordering that we talked about, the coarsening, the coarsening that we defined in order with E of x0, E of x1. Okay, so thinking about how this relates to what we're going to end up trying to do, what is the idea here? The idea is we see from these two parts of the definition that we want to be able to have a sufficient supply of such functions that are n elevators. We're going to want to have such things for every natural number n. And the idea is that we've got this combination of properties. The first property is the one that helps us do something regarding the tree itself, because by doing this, we're going to ensure that the tree will end up somehow being finite to 1 by making sure we have enough such things. And the second part has more to do with how we're going to control the properties of the square of the tree. Okay, we want to be able to, I mean, again, we'll see how it works what we do eventually in the construction, but this has more to do with the properties of the square of the tree. We want to ensure that as we go up, we have a sufficient supply of such elevators, n elevators for every n. Well, the second clause doesn't depend on n, but the point is we have these elevators where we always maintain pairs above that satisfy this this property, order property with relation to the nodes that already exist. Okay, so we're going to talk about constructing, making sure we have elevators.
Coarsenings. I mean, is it the case that coarsenings are simply the usual partial order restricted to a subset? Or is there another example?
Yeah, I don't know. I don't think we want to just restrict it to a subset, because I think the problem would.
So what would an example?
Well, we'll see. We'll do when we get to the one that we actually use. There's only going to be one, so we'll see the one that we actually use.
Sorry, but I thought coarsening was on the same domain, that you're not going to small domain. You're just coarsening.
Yeah, no, it's the same domain, right? No, it's the same domain. Some pairs, right? This is a this is an if then, it's not if and only if. So there are some pairs where you may have, or pairs of pairs, whatever you want to call it, right? You may have a pair less than a pair in the usual tree order, but they are not considered to be one less than the other in the coarsening order.
A subset of the usual.
Oh, of the ordering, is that what you said? Okay, it's definitely, yes, okay, it's a subset of the ordering, yes. Sorry, maybe I misunderstood that, yeah.
It's pretty close, right? You do capture kind of intervals like this.
And you want to have, right, exactly, you want to have that
Maybe
as well.
Like maybe you cut off the bottom somewhere. And then
We'll
cut
see.
off the top somewhere.
Or
It's stuff you fill in.
specific nodes that we want to exclude, or we'll see how it works. We're going to want to exclude specific nodes, yeah. Okay. And let's just make a remark. Where am I up to next on the board? I'll go over here. A remark that will be turn out to be useful to keep in mind. If you compose two elevators, you get an elevator. And in particular, with regarding the number n that it depends on, hang on. So I can just make the statement generally here. Where did I write it? Okay, remark. Okay, the composition of an n elevator with an m elevator for any two numbers, elevator is an, which way did I write it? Is a min mn elevator, because the only part that depends on the number is this thing right here, Okay, and these sets are closed in one direction or another, in the direction that gives us this. Okay. Okay, so let's now define coordination. Okay, when we build a tree, we're going to want to know that any two levels that we've constructed are coordinated. Okay, what do we call here coordination? We're going to say this here for a tree. For a tree T, a coarsening or a tree coarsening. A tree coarsening of there and ordinals beta less than alpha up to the tree, up to the height of the tree. What does it mean for the levels at beta and at alpha to be coordinated? Okay, we say that T beta and T alpha are coordinated, and there's obviously an implicit dependency on the tree coarsening, but we won't say it all the time. If for every n, for every number n, we have the following three conditions hold. Okay, number one, where am I? Number one is for every finite set W at the alpha level, W is going to be a finite set of things at the alpha level that we're going to want to exclude. We want to talk about coordination has to do with the existence of elevators. We want to assert that sufficiently many elevators from T beta to T alpha exist, satisfying what? So we want to be able to exclude any given finite set from the image. So we want to say for every finite set of the higher level of T alpha, there exists an n elevator E from, I can even just say it this way, from T beta into T alpha minus W. Okay, so an elevator from T beta to T alpha that avoids the finite set W that's given. I'm going to need to go over here somewhere for the next couple of clauses. And just realize right away before I even state the next two clauses, just based on the first clause, this is already a strong form of normality, right? Because, well, in fact, you're saying even with any one of those, you've got some not topological normality. Sorry, I shouldn't have said that. Normal in the sense of tree. We've just got that every node has extensions at every higher level, right? And in fact, infinitely many. I shouldn't have said normality. That's the bad word here because it means something else. What?
That's not normality. Normality is the one where you know, if you have two nodes with the same predecessors, that they are the same node.
Never mind. Okay, it doesn't matter. I skipped the word. I shouldn't have mentioned the word. It's not relevant. All I wanted to say is that we clearly know that number one is a strengthening of the often desirable property that you always have extensions of nodes at every higher level. It's what Kunin calls well pruned in his somewhere along the way. But we'll leave that aside. But notice here that it's not just that every node has extensions, but every node has infinitely many extensions because we're doing this for every n. And so once you do that, you're going to get infinitely many extensions. But okay, that's clause number one. Okay, clause number two in the definition of coordination here needs to be for every node at the beta level, okay, every node x at the beta level, every y that's in the UNX at the alpha level, okay, and every finite should have written, it's not going to work here. Every finite W in the alpha level, but not including that node Y. Okay, we want to say there's an elevator. There is an N elevator from beta level to the alpha level without W, such that the E of X takes you to Y. In other words, if we fix in advance a particular node at the beta level, particular node at the alpha level, it needs to be in here so we don't get a contradiction for where we want to go. So we can find an elevator taking X to Y and also omitting a pre-designed, a pre-given finite set. Okay. And then the third condition is essentially doing the same thing for two nodes at the same time. But in this case, we want to talk about the coarsening order. So we'll say it here for for every pair x0, x1 in, so every pair of distinct nodes, x1, that would hell yeah, every distinct pair at the beta level. Okay, every also pair y0, y1, again distinct at the alpha level, but not just that. I don't want them here, sorry. In what I want them to be specifically, such that, let's do this right, the y0 should be in u n x0 at the alpha level, and the y1 should be in the u n x1 at the alpha level, and such that they maintain the correct ordering, meaning that x0, x1 is in the correct ordering that we want with y0 and y1. Okay, and again, every finite set that we want to avoid, finite W in T alpha, but this time omitting the two nodes that we've designated ahead of time, y0, y1. Okay, there exists an N elevator. There exists an elevator from T beta to T alpha, or again, T alpha excluding W, such that the things go, the pair go where it goes, where it's supposed to go. In other words, E of x0 goes to y0, and E of x1 goes to y1.
So, but in two, you didn't require the coarser order.
Correct, because the coarser ordering is only defined, the tree coarsening that we talk about is only defined for pairs, right? The coarsen.
X and Y would have been the coarser. I would have thought.
No. A tree coarsening,
Oh,
it's a coarsening of the ordering on pairs. So it's not meaningful to talk about that ordering, comparing a single node to a single node. That ordering is only meaningful to talk about comparing a pair at level beta to a pair at level alpha.
Is condition 2 just stronger than condition 1?
I think it's almost, I think there was some edge case where we couldn't just omit one entirely. And I think that was because I had some reason. I know I thought about that too. It almost does. And if you like to think it does, it's probably not bad. But there was some edge case where it actually mattered that I had to write one and not just write two. I think because maybe something's empty. What could be empty here?
Well, you want to hit this point, right? So this one, the elevators can be small, but here you're insisting that you can hit any given point. So it is formally stronger.
So could I omit one? Just a minute, for every finite set.
No. What was that the question?
Yeah.
Well, I think that's what you were saying. If
sorry,
maybe I'm right, maybe if we can omit, it won't matter in the end. If it turns out we can omit one, then fine. For some reason, I thought of it, and I think that I had some reason why not. But if it turns out to be wrong, I won't be too upset.
I mean, maybe levels being finite or something.
Well, we're always going to do infinite. Our trees, no, but they can't be because once you build
Once you know the first.
right, right. What was the reason? There isn't an elevator for every x, every one. Well, what if okay.
X could have finitely many successors, so that level, that's the issue. Because elevator goes into those successors. But why would you?
All right, maybe 2 implies 1, in which case, just think of it that way, it's fine.
Oh,
Okay, maybe that's the more sense. No, I don't think so. I know that I'm pretty sure is not, because you're dealing with the coarsening here, which is an entirely different. Yeah, that's well, it's a different feature on the hypothesis here, right? You want 2 to be true for x and y that are where the y is above x involving the u. We didn't mention this u. Oh, we did. Sorry, where the y is above x in the u, but we don't say anything about how pairs are related.
Pairs unless they are ordered.
That's the point, right? So we do need 2 and 3 clearly say something. Each one says something important that the other one doesn't cover, I believe.
Is the issue that you haven't said that U and X might be empty? I mean, then you would need 1. If there's
Maybe that's the point.
But
If U and X is
you haven't
empty,
said anything about U and X.
maybe that's the point. Yeah, maybe that's the point. This could no, but we're always gonna. I think we're always gonna construct it so that it isn't.
So that's what it was.
So in the end, maybe it doesn't matter. In the end, maybe we could get away without 1. Could possibly get away without 1. Okay. Okay, so I think we're just about ready for the actual construction. Which you want.
So far, you just said that there are lots of elevators.
Well, we want to build a tree with lots of elevators. That's the point.
How?
Oh well, no. Okay, the where am I?
I mean, you don't have any restrictions on.
Hold on.
You can just
The
throw
concept
anything
of
an elevator.
I should okay, coordinated. We're defining here coordination, right? The concept of coordination is an assertion that there are lots of elevators. Right. There are lots of elevators, and in particular, lots of elevators with these particular features that we can control where they send, that we can control, that we can send an individual node to an individual node that we want to above it, and that we can send a particular pair to a particular pair that we want to above it. And at the same time, that we can avoid any given finite set. Okay, makes sense? Pardon me?
It's gonna matter a lot.
Yeah, okay, so let's do that. Okay, let's get there. Okay, so yeah, that's okay. So let's actually talk about the construction, and let's say here. I know there's not a whole lot of time left. I hope we can at least get to, even if we can't prove that the tree satisfies all the desired properties, I hope we can at least see what the construction looks like and get some hints as to where that's going to take us. Okay. So, oh yeah, one important property that we should mention here is coordination is transitive. You can more or less just work through it case by case. I'll just write it down here. The proof is longer to write out than what it actually takes to think about. It's really just kind of, so I'll write it here as a remark. Coordination is transitive. Okay, if I've got gamma, beta, and alpha, T beta and T gamma and T beta are coordinated, T beta and T alpha are coordinated, then T gamma and T alpha are coordinated.
I mean, that's your remark already about the elevators being the composition.
Yeah, it's based on that. Yeah, exactly. The composition of an elevator does what you want, so everything else just fits. Everything else just flows. Okay. Oh, right. I need to talk about, so let's do the actual construction. I need to talk about, though, how we're going to use diamond. I think okay, let's do that quickly. Okay. Okay, to apply diamond star, which is what did I?
Yeah, you have. I was going to ask, why don't you use diamond?
No, it's going to be diamond star. Yeah, no. When I stated the theorem, I believe I stated with diamond star, right? Yeah. Okay. To apply diamond star, okay, we use 2 of its consequences. Okay. Guess I'll write them separately. Okay, here we go. Let's see here. So let's just say diamond star on omega 1 implies that there exists a sequence C alpha sequence, essentially a C sequence here, such that, what are we going to say, for every limit ordinal, okay, C alpha is a cofinal subset, it's the easy thing, of alpha of type omega. Okay, but but in particular, okay, for every uncountable B in omega 1, we want a certain hitting property. Okay, there are club many ordinals such that sup of C alpha intersection beta equals alpha. Okay, I was just wondering if I was supposed to say the knack here. I could put that in, but okay. Club many. So we've got a certain hitting property. And this is one of the ways we're going to implement this sort of the hitting property of diamond. Okay, we build a C sequence, single sequence at each alpha, and for any uncountable set, it gets hit at club many places. And by hitting, we mean that at every such alpha where the hitting takes place, there are many meets. There are many ordinals where the C alpha intersects the set beta that we're trying to hit. Okay, it's a weakening. You could think of this. It's a weakening of what we might think of as diamond. This is not obviously this is weaker than diamond itself. I'm sorry, weaker than diamond star. You wouldn't get club many from a regular diamond. So we need the strength of diamond star in order to get club and not stationarily many. But this is not the full prediction property of diamond that you would expect. It's weaker in the prediction sense that we're not claiming that C alpha intersection or that C alpha exactly predicts the initial segment of the set B, but rather that it has a cofinal set of meets with it. Okay, but there's a second important property that we need, which comes from diamond in this case. Where am I going here? Am I moving this forward, right? And this comes from the fact, I'll just say briefly here, or whenever we're gonna, okay, we'll just try to say quickly. The next one is really about diamond. We would work with it's an equivalence of diamond, not needing the diamond star, but just so we know, diamond predicts subsets of, or diamond as we in its usual formulation predicts initial segments of sets of ordinals. But our trees are not ordinals, they're sequences. And you see all throughout the literature people doing like reformulations of diamond, encoding other things in terms of encoding subsets in terms of ordinals. So let's just do it once and for all in a general way. Okay, diamond omega 1 is equivalent to the existence of a partition R, what do I call it? I less than omega 1, and sequence, we'll call it omega alphas for alpha up to omega 1, such that, sorry, this is a sequence of countable sets.
In partition of omega 1.
Sorry, I should have said, yes, correct. A partition of omega 1 and a sequence of countable sets such that for all, now what do we have here? For every parameter in H omega 2, every ordinal I up to omega 1, and every subset omega in H omega 1, okay, there exists a countable elementary submodel M of H omega 2 such that the parameter is in the submodel, the intersection of the model with omega 1 is an ordinal in Ri, and M intersection omega. This is basically saying that the M, the elementary submodel gives, sorry, that the omega beta from the sequence of predictions here, okay, predicts an initial segment of omega. We can think of it this way. Diamond in general predicts any subset of ordinals by means of its initial segments, okay? Here we want to be able to predict not just sets of ordinals, but any sorts of objects of size omega 1. So if we think of any object of size omega 1, like our trees, as being, they are essentially encoded as, or they are basically subsets of H omega 1. So let's say omega, the big O capital omega here is our tree or an anti-chain or whatever it is that we want to be able to predict. It's a subset of H omega 1. The sequence of this is essentially our diamond sequence. It's a set of predictions indexed by omega 1, but these items are not sets of ordinals. They're sets of all sorts of countable objects. Okay, they are countable sets of countable objects. Okay, and so we want to say there's some elementary submodel that allows us to say that we've captured the thing we're trying to predict up to the elementary submodel by the prediction omega beta from the sequence. I should have called this beta here. I don't know why I said alpha. These should be betas. Okay. Okay, so that's how we're using omega. We got to already get to some construction in 5 minutes or so. So let's see what we can do. Okay, so we want to prove the theorem number. I forget now if it's 1 or 2. I think it's theorem 2 we're going to do. Okay, proof of theorem 2. And we want to do the tree construction. Oh, I could have erased something up there, right?
So I'm not, what is the R, where are the partitions?
Oh,
here?
here. So
It's somewhere. Here.
I is any given I. So for every I, okay, if you think of this without the Ri, then the I here doesn't matter. And it's still a way to generalize diamond to work on arbitrary objects of size omega 1 rather than just ordinals. Okay. And the fact that we're adding in this partition allows us to say that we want the hitting to occur in a pre-designated slot of the partition. We're kind of partitioning or getting a partition of omega 1 into uncountably many sets so that we can control where the hitting will occur, where the hitting will, so that we control the hitting will be in one or the other or in any pre-assigned set of the partition. Okay. I got to jump because I'm not going to get much farther. Let me just see how we can. All right, I may have to skip some of the encoding aspects, but we'll just try to focus on some features of the construction so that we can actually get somewhere. Let's just see. So what is the coarsening? All right, let's just see, we can see what the coarsening is going to be. We want to construct a T. Okay, so the construction of the tree T that we're looking for, in other words, proof of theorem. I guess it's theorem 2. All right. Whether I should I'm going to skip some preliminaries and just try to get to the details. Okay, so we're going to fix sequences as in, we're going to fix this C sequence here, and we're going to fix the sequence of omegas here and the sequence of the partition of R here as in those, as in the hypothesis. All right, fix, what do we call it? Yeah, C and the omega betas and the Ri as above. Okay, a couple other technical things. Let's just say, okay, what's the tree coarsening going to be? This is going to be interesting, important here too. What's the tree coarsening? Okay. Hang on. No, okay, along the way, let's just say this here. We shall construct recursively the levels of the tree of a finite to one tree T. Okay, along with, here's what we're going to say, along with a subset E of ordinals. That's going to be important for us. We're going to, as we go along, we're going to decide which ordinal to throw into E and which ordinals not to throw into E. I should have said here, finite to one, of course, L with one tree, right? Okay. And as well, and an anti-chain a epsilon for epsilon in the levels in the ordinals of E, where each so these have to be in the correct levels. Maybe I should use a better symbol than that. At the epsilon. So we're going to construct an anti-chain along the way as we go of but an anti-chain in the usual in the square of the usual tree ordering, but specifically only for ordinals at the levels that we put into E. Okay. Now the point is that this anti-chain will then induce our tree coarsening. This anti-chain will induce our tree coarsening. So let's just say this here quickly. This anti-chain, okay, will induce a tree coarsening by setting okay, XO, X1 is in the coarsening order with Y0, Y1 if, okay, two things hold. I'm going to call them here Aleph and Bet. Okay, we want, of course, that you have to maintain the true ordering, or the has to be right. And what are we going to call it? For every j less than 2, just so that we can permute the pairs if we need to. Okay, if, let me write it this way. If A epsilon is not comparable to xj x1 minus j for every epsilon in the E up to the level of x0, up to and including the level of x0, okay, then A epsilon is incomparable to yj, y1 minus j for what can I write here? For every epsilon in E up to the height of y, up to and including. Okay, so if So we want to say the two nodes are, two pairs are comparable in this ordering if for the anti-chain that we've defined up here, the anti-chain that we've defined up to this point, okay, if everything in the anti-chain is incomparable with the lower nodes, then you don't want to add any comparability as you get up to the higher node. Okay, I'm not sure how much more time there is and how much more we can, oh, there isn't even really. I'm not sure how much I can say. I was hoping we could do something about the construction, about the,
No, if there's no A epsilon below, you don't want to move up to something which is above an A epsilon.
correct. Okay.
That's the usual thing you're capturing, that's why I'm saying at some level, trying to maintain passing through it.
Something along that kind of line, yeah.
But you're only doing it for the first coordinates.
No, because the domains match. This is just a notational trick. When I say domain of X, for a pair to be in, we're talking about an anti-chain, I should have said in the square of the tree, right? This is an anti-chain. This is an anti-chain, I could have said here. Yeah, it's in right. Two elements always have the same, these two have the same height.
Yeah, but
So the domain of X0 is the same as the domain of X1. It's just a notational word.
Domain, that's what
Yeah.
you said. Okay, but A epsilon is an anti-chain.
It's for every epsilon up to the height of, if for every epsilon up to the height of X0, all of those A epsilons are incomparable with the X pair that we're starting with. Then when I get up to the height of Y0, I want all the further ones to remain also incomparable, not anything new that's comparable.
But can't you just delete both of these for every blah blah? Because of course, if epsilon is greater than that, it's not going to be below. so isn't it redundant?
Okay, but I have to quantify the epsilon somehow.
Well, for every epsilon in E. I mean, you don't have to say about domain, right? Because if E,
Yeah, you're
not
okay.
there,
The problem is that
Not there.
okay. The problem is at the recursive stage of the construction, E is only defined up to, let's say, domain
I
of Y
see,
plus
okay,
one.
okay.
So I need it's a bit of a notational quirk. I need to say something. I can't just
okay,
say.
at the end of the day, this is what you get.
Yeah, that's what we have. Yeah.
Okay.
Okay, so I'm not sure. I guess I'm kind of out of time, right? I just was going to say something quickly because I haven't done the crux of the construction. But let's just okay. I'll just give a 1 minute. I'll try to just say something briefly about how we eventually do the construction without giving the details. That's not so easy. But I just want to give a couple of comments. We're going to use these sequences. Where are we here? We're going to use these sequences. Okay, at every successive stage, you just add as many things as you need, and things should be coordinated. That's not a problem. At the limit stage is where it matters. Okay, and so at the limit stage, we build along the appropriate C alpha sequence. Okay, and we want to build a sequence of nodes leading up to level alpha, whose limit we will then put into the tree. Okay, we want this construction to satisfy several features as we do it, and this is how everything kind of, all the pieces need to, all the ingredients need to come together. Okay, what we're going to do is we're going to use the prediction of the omegas here, omega betas, and also the partition here. Okay, and the idea basically is that if omega beta predicts some kind of an anti-chain of the tree up to that level, then we want to some way or other go through the anti-chain while maintaining, I have erased it already, while maintaining for example, the U being in the certain U and X sets as appropriate in those open U sets, so we can guarantee the kind of thing like that's how we're going to get the first. That's how we're going to eventually, with enough such predictions, get the tree to be finite to one and therefore are embeddable. Okay, but at other stages of the construction, we're going to want to go through we're going to want to see what happens if essentially omega beta predicts something, a set of pairs below the level that we want. Because remember, omega beta is these very flexible predictions. Omega beta is a set of things that can basically predict anything of size omega 1. Predict initial segments of anything of size omega 1, right? The idea of diamond is anything of size omega 1 will be predicted sufficiently often along the way. So at some stages, we use it to predict properties that will help us for the tree T itself. At other stages, we will use it to predict properties of the square of the tree. And the idea is that we can control both of these sufficiently often to make it work. Okay, a feature of the construction is, of course, that we're going to maintain the coordination along the way as we build all the levels, and more or less that's how we're going to do it. I'm sorry that I didn't get a chance to quite, fill in the details there, but I guess the time is kind of gone. So I think that's the best we can do for now. We do have a preprint available, and the preprint actually does the more complicated version, which is the theorem 1 rather than theorem 2. So I invite you to all to have a look and see what we can see what you can see. I'll be happy to talk a little bit some more later. I don't know, any questions so far?
If I'm following, so you're first building this tree with this ordering and all those elevators, and then you use elevators to build something else.
No. We do it all at the same time. The whole point of the recursive, we're doing the recursive construction where you do everything simultaneously.
Okay.
And the point is, at every one, okay, let me just clarify this one point. At any one ordinal alpha, to build the alphth level, assuming alpha is a limit ordinal, to build the alphth level of the tree, we go along the C alpha sequence of ordinals, and we choose carefully which nodes at each level of the ordinals in the C alpha, okay, where at some ordinals we'll do it to control the properties of the tree itself, and at other ordinals, again, all below alpha, while we're building the alpha level, we'll use the choice of the node along the branch, the choice of the branch to control the properties of the square of the tree. So by the time we're putting a node, any node, into level C alpha, we have already guaranteed or confirmed some amount of control over both aspects of what it is that we want to construct.
And you're using the elevators below to get up to C alpha, but then
Yes.
also having to build the elevator to C alpha.
Yes, we are guaranteed, right. When we build level C alpha, we are using the coordination of all pairs of levels below. And as we build the C alpha, we will be able to guarantee as well that C alpha, the level alpha, so as we build T alpha, level alpha of the tree is coordinated with all the levels below. Yes.
So when you're using diamond with the R's, my guess is that you're just going to use a partition into 2 pieces for your argument. One is for the tree and the other for the square.
In the end, we end up doing it a little bit more with some more pieces, but it may not be as essential. For the most part, there are, okay, hang on. For the square, we need one partition. I think for the others, we end up encoding. We end up encoding all the nodes of the tree along the way as ordinals and then using them as part of the partition as well. So it ends up being a little bit more subtle than that. Because we need to make sure that I guess part of getting the almost Suslit, well, everything in conjunction. I guess we need to make sure, yeah.
You need above a node of a tree, things happen.
Exactly.
So you visit that.
Yeah, right.
Okay, thanks very much. Let's vacate and go get some coffee. Get Bob outside.
Thanks. Thank you all. Thank you all for listening.